morning, everybody. So first of all, apologies for not being here earlier. I had teaching on Monday, which is why I couldn't get here any sooner. So thanks for bearing with me. What I hope to do over the next 45 minutes is to try to give you some general perspectives on how to use high-performance distributed computing. That's what HPDC stands for. And I'll try to show you first in the concepts, the underlying abstractions, but obviously then try to specialize into scientific problems of interest to you. And primarily, the middle graph that I want to talk about is what I want to work towards. So what is the middle graph? The middle graph is a model, is a simulation of a model which you're all very familiar with using WRF. It is on the x-axis, there are a number of ensembles, and we'll run not one, not two, but we'll run up to 64 ensemble members. And on the y-axis is the time to completion, and we'll run this over a very large number of cores, starting from 16 cores all the way up to several thousand cores. And I want you to appreciate over the course of first the 45 minutes general lecture, and then over the course of the next 45 minutes when we do a hands-on lecture, a hands-on session, the power of abstractions that will enable you to run simulations that incorporate 64 WRF simulations concurrently running on very large machines of the type you've heard, for example, in Munich or some of the largest supercomputers in America. So that's where I want to lead you. Also want to tell you just one thing on the side. Obviously, the DRIHM project, you've obviously heard of the DRIHM to US project, and you've probably heard earlier talk about the SCHEME project, which is the standards-based cyber infrastructure for hydrometeorology. I come here wearing the SCHEME hat, and I will come back and talk to you a bit about the S in SCHEME, the standards, and you can see that that also has a prominent role here. So with that, let's get going. On this cover slide, you see that these tools that I'm going to talk to you about, the Cybertools, are obviously used for hydrometeorological simulations, but they're also used for a large variety of other domain sciences. And what you see on the two sides are biomolecular simulations, large uptake there. And what you see on the lower side are three, obviously I'll get into details later, but three architecture schematics of the Cybertools. For the purposes of this lecture, we'll focus on just two, Radical Pilot and Saga. We will not talk about other examples, but I'd be more than glad to talk to you, anybody offline, if they wanted to. Right? Please note the URLs. Everything I say, everything I'll talk about is available for download and testing. Okay. So let's get started, and let me just very quickly, again, maybe a shameless advertisement, try to give you a 30-second overview of what my group does. So the group is, as you've probably figured from the previous slide, called Radical, and we focus on a large number of areas, primarily using high-performance distributed computing, but we focus on applications, scientific applications, e-science applications, as we would call them this side, and we try to think of how we can design systems, middleware, so as to enable the scalable execution of scientific application. This requires thinking of algorithms, this requires thinking of implementations of abstractions. This obviously requires thinking of the scientific applications themselves. So if you will, the triple point of applications, theory, and infrastructure. And many different examples of what kind of specific problems we work on in order to make this happen. Okay, so let's give an outline of today's lecture. I'm going to actually begin by trying to talk to you about task-level parallelism. Spend maybe 5 to 7 minutes reviewing some of the concepts in case you had not been exposed to this. In a nutshell, task-level parallelism is the ability to run many, as an example of task-level parallelism, the ability to run many different ensemble members of WRF at the same instance. So the 64 simulations that I alluded to, that's a very simple canonical example of task level parallelism. There are other examples which we'll talk about. I will then proffer as a natural abstraction to simulate many simulations, the pilot concept. Some of you may know what a pilot job is, but I'll take a few minutes to try to describe the pilot concept more carefully. Then I'll give you specific examples of the pilot job system that we've implemented and try to show you how it is distinct from other possible pilot job systems that you may have heard of or you may encounter. Then I'll try to go straight, very quickly, talk to you about one or two very simple examples of biological science, just for variety, just for diversity, before giving you a bit more details on that graph that I teased you with right in the center of my opening slide. There probably won't be time, but I will leave you with a few extra slides just to try to show you the advantage of an abstractions-based approach. We can solve the problems that we want to solve right now in scalable fashion, interoperable ways, but the use of abstractions, the use of carefully designed building blocks allows us to then start extending what we're able to do to other application types, other application requirements. And I'll just, again, tease you with some different examples of this extensibility without giving you many details. So that's the outline. So let's dive right into task level parallelism. And just to kind of set the stage, task level parallelism, like other types of parallelism, whether you talk about thread level parallelism or, if you will, process level parallelism, is a type of parallelism which allows you to run many concurrent tasks at the same instant of time. A task here is essentially a standalone simulation, a standalone kernel, a kernel being the executable that you will run. So again, just to be clear, I will often conflate task level parallelism with task level concurrency. I will also at times say simulations, many of them, and I'll conflate simulation worth with the kernel that you're actually going to simulate, right? So the ability to run many such simulations, many such kernels at the same instant of time is what we're going to concern ourselves with over the next 40 minutes. And we want to do this as scalably as possible. Scalable, again, many different dimensions here. Scalable in the number of ensemble members, the number of simulations. I showed you a graph of 64. There are people who want to run 10,000 tasks at the same time in the biological sciences domain, and I see no reason why people in the art field here would not want to run up to 10,000 simulations at the same time. But there are other dimensions of scalability. They could be along the number of cores, and there could also be the dimension of scaling out the number of resources you want to concurrently utilize. So scaling is a multidimensional parameter or a multidimensional metric, and we'll come back to this, the different dimensions of scaling later. So now let's come back and remind ourselves why task level parallelism is such a simple but such a critical conceptual construct. It so happens that a very, very large number of computational science and engineering applications are amenable to task level parallelism. So embarrassingly parallel is another term you'll have heard, and ensemble scenarios, if you want to lower the errors, have better predictability, you want to run not one scenario, you want to run many scenarios, but each of these scenarios are decoupled from another, right? And that's why it's often called embarrassingly parallel, because they do not actually couple to each other. So that's one very common, I would argue, the most common scenario that I'm sure many of you are familiar with. The second scenario that task level parallelism often arises is in uncertainty quantification, where again it's a slight take on the embarrassingly parallel ensemble scenarios. You have a non-fixed number of scenarios, non-fixed number of simulations that you may need to run. Variations of the uncertainty quantification scenario may lead to non-identical simulations, and these are typically found, for example, in the multiphysics domain, but you have many of these simulations. So I hope you get the drift. The need for running many different, simulations, possibly similar, possibly distinct, arises all over. And again, in the free energy, in the biological sciences, you never know how accurate your simulation results are. You can lower the statistical errors, but often you're not able to get a handle on the systematic errors. And this is what in the biological sciences is called the sampling problem. I know there are variations of this problem in many other domains where you just need many simulations before you can get a handle on what part of phase space you're in. So that's often called the sampling problem, which again, you have to run many simulations. So hopefully by this stage, you've got a handle on the fact that task level parallelism is a very powerful construct, commonly found for many different science and engineering applications. So no surprises, we're going to pause and think of how to support task level parallelism effectively and efficiently. Just before I go further, just want to point out that even where applications may not naturally be amenable to task level parallelism, it has been shown that you can solve problems which otherwise could not be solved efficiently by converting them through algorithmic transformations into task level parallelism forms, and you're able to then solve the problem more efficiently. And this is just one example of a problem that I worked on for about 3 to 4 years, where we took one very long running simulation over 1,000 cores approximately, and converted that into many shorter simulations, same number of cores, but many shorter simulations, but a large number of them. And the science that was not possible with this one very long simulation was then possible with many smaller simulations. And that's all that I referred to, where you might convert or think of converting a single large application into many smaller applications. Not always easy, but worth your thought, worth your time. So with this, we move on to having motivated the importance of task level parallelism, motivate the fact that it may seem simple, but it is the basis for constructing and executing many more complex applications. So I often at this stage, at least by the computer science community, get told, you've just reduced very difficult problems into the simplest problem, namely running many different tasks. I say, yes, I've done that, but that's in order to enable me to walk before we start running. And interestingly and importantly, by reducing a large set of applications to task level parallelism, I can then rebuild the full complex problem along 3 dimensions. So think of the point of running many coupled simulations as the 0 point of this 3-dimensional space. Think of the 3 different dimensions or axes as representing dependency, homogeneity versus heterogeneity, the H, and then the C as coupling. So let's talk about each of these dimensions for a second. So I've talked about a large number of simulations that are uncoupled, that do not depend upon any other aspect. So you just have a batch of tasks and you run them. Think for a second of a batch of tasks that run, and then another batch of tasks that need to run, but only after the first batch has actually executed. You've introduced the first simple dependency, but now not a dependency of one task on another, but an ensemble of tasks on the previous ensemble of tasks. So that's what the D stands for, simple, and then you can obviously have variation of this complex dependency. You might have partial dependency, you may have complete dependency and multi-stage dependency. You can let your mind run along how complex you make it. The H is quite simple. I started off by thinking and talking of all the tasks as uniform, as homogeneous. You can think of the tasks as a knob, which then changes the types of tasks. So some tasks are very similar, some tasks are extremely distinct, and obviously the spectrum from similar tasks to large tasks. So you could have, if you will, some tasks that are single cores running for a short duration. You could have some tasks that are highly, let's say, adaptive, requiring lots of many cores, and the time duration of them is not predictable. So predictable small cores simulations, unpredictable large simulations. And obviously when you have a bag of these tasks with varying characteristics, then managing the effective execution of widely varying tasks becomes harder, right? If everything is uniform, if we all walk and run at the same pace, then it's very easy to predict when we'll get from here to dinner. But if we all walk at very differing paces, then predicting the time when we'll all get there is not going to, or how quickly we can get there is going to be a more challenging task. So the same thing applies here. Let me then talk about the third dimension, coupling. So far, I've talked about independent walkers, independent ensemble members. However, you could have these ensemble members not entirely independent, but possibly exchanging data, possibly exchanging state, possibly exchanging some information. This adds significant complexity to the situation when they're all running decoupled. Please note the distinction between dependency between stages and dependencies within a stage. The dependency within a stage is what I'm calling coupling between tasks of the same generation, of the same stage. And the dependency between stages is what I'm talking of as it's important to distinguish these two different types of dependencies and coupling. So with this long-winded kind of theoretical construct, what I want you to take away, if nothing else, is that by reducing the problem space to a set of tasks, initially uncoupled, initially non-dependent with each other between stages, and initially homogeneous, you can recompute the full complexity by adding varying amounts of D, H, or C. Okay? And then you are mimicking real workflows. Okay, so now I start speeding up remember what our goal is to take a bag of tasks and to map them efficiently and effectively onto resources. Now it's important to appreciate that you may have different types of bags of tasks, different types of tasks, and you may have different types of infrastructure. So fundamentally, what you want to aim for is something that is not dependent, an approach that is not dependent on any given, if you will, parameter of the phase space you might be in, whether that phase space be in the application space or on the infrastructure. Said in other words, I give you 10,000 cores. You want to be able to splice and dice those 10,000 cores in any way that is required by the application. So if I give you 10,000 cores, one day you may say, I want 100 ensembles of 100 cores each, which is 10,000. On another day, you may say, I want 1,000 ensembles of just 10 cores each, which is still 10,000 cores. And on some day, you may say, I want 10,000 ensembles each of one core, which is 10,000 cores each. That's what I mean by slice and dice in any way possible. And depending upon which of these three examples you want to, let's say, implement, you don't want to have to use a different set of tools. You don't want to have to use a very different methodology. You want the same approach independent of your ensemble size, independent of the number of ensembles, and independent of whether you get your 10,000 cores on one machine or 10 machines or 100 machines. I hope you see the objective of what I'm trying to say here. You want at a logical level to be able to map a large number of tasks onto a large number of cores, and you want to do this mapping in a conceptual way that is independent of the underlying implementation and the tools. Is everybody with me? Does this, because this is the critical point of everything that follows from here out onwards. Okay? So once again, one last time, what you're trying to do is you're trying to map a large number of tasks onto a large number of cores, and you want to have a conceptual mapping of these tasks onto these cores independent of the specific infrastructure, independent of the specific size of the task, and obviously independent of the number of machines you want to do this mapping over. And this is why we introduced the concept of an abstraction, in which in this case is the pilot abstraction. So having motivated the need for this abstraction, let me speak to what this abstraction is. So the pilot abstraction is a system that generalizes a large placeholder job, a logical placeholder job, to provide multi-level scheduling, and I'll get to that in a second, that allows you to map any number of tasks onto any number of cores onto any number of resources. Let's have an example. Let's work through this example. So think of all of these small oval circles. It should actually be a circle, but because of the ratio, it's looking more like an oval. You want each of these circles to be, which represents a task, to be executed on a set of resources. So what you do is, instead of submitting a task onto a specific resource directly, which is what you've been doing, what you do is you submit these tasks onto pilot jobs. Remember, pilot job is this container job that will go onto a resource and will act as an overlay over all the different number of resources. So you could have 4 resources, but from the task's point of view, i.e. from the user's point of view, all 4 resources are presented as if they were a single resource, right? And the way this happens is the pilot job goes onto 2 specific resources, again through something called a resource manager, which we'll ignore, right? And so you've now got the pilot job system running 2 empty jobs on 2 resources. And you don't, as a user, need to worry at this moment where these jobs, these empty pilot jobs are running, empty container jobs are running. All that you need to worry about is submitting these 2 tasks into the pilot job system, which then gets directed onto the resources. So note what I've done. You had 2 tasks which you did not submit directly to the resources, but you submitted via the pilot job system on these containers. Your responsibility is not to figure out the resource. Your responsibility is to onto the pilot job system, who then in turn is responsible for submitting the tasks onto the appropriate resource. Okay, so let's generalize that. So I can go through that again, but again, to generalize that, the pilot abstraction is a generalization of the recurring concept of using a placeholder job as a container for a set of compute tasks, which then are placed onto the appropriate resource. So what are the advantages? So I'm going to show you how this very simple concept actually enables the objectives that I alluded to here. Okay, so that is what I'm trying to work through over the next 10 minutes, how the objectives here of given access to X cores or nodes, slice and dice or distribute as needed, right? I'm going to show you how this concept actually leads to that, right? And to try to step back for a second, what I'm trying to talk to you about is the importance and the requirements of flexible resource management, right? And importantly, decoupling the workload or the set of tasks from the specific set of resources on which they will run, as well as the management of those resources. Once again, what I'm trying to tell you is that the simple concept that I've just outlined, the pilot concept, will enable you to decouple your tasks from the specific resources on which they will run and the management of those resources, as well as allow you to utilize these resources in a flexible manner. Okay, so enough of theory. Now let's get into, so let me actually pause for a second and take questions. Is everybody at least conceptually familiar now with the basic concept of a pilot abstraction? If not, I'm happy to go back and just quickly, because a lot of what we're going to do is going to be actually playing around with the pilot job, so no point playing around with the toy, which we don't understand. Any questions? I see faces varying from convinced to confused. Okay. So what I'm going to do I think I have 20 minutes left, what I'm really going to walk you through is some examples of how the radical pilot, of what the radical pilot is and how to get access to it, so that when we go into the tutorial, we'll be well placed to play around with it. So no surprises, the radical pilot, as the name suggests, is my group's implementation of the pilot job concept. So everything I've showed you earlier is a general concept. Yes, our group has formalized this concept, kind of developed the theory of this, but the concept has been around, I think, for at least 15 years, long before we stepped in and started implementing this. So the pilot job concept, I think, traces back to the early 90s, maybe mid-90s. And what we've done over the past few years is formalize it, kind of put it onto a firm footing, theoretical footing, and then implemented it. And this implementation is what I call what we call the radical pilot. We'll come back to this diagram later. I just want you to understand that there is a well-defined API which we'll be playing around with in a short duration, and the concept of a pilot agent. The pilot agent is what I was earlier referring to as this container job will actually be the pilot agent, which we will play around with in a short while, right? Okay, so enough toing and fro. The other point I want you to understand is this yellow layer called Saga, and this will again be how we make Radical Pilot interoperable so that it works on grids, clusters that are distributed, supercomputers of the type that you've seen at SuperMOOC and elsewhere, clouds of the type that you're familiar with, Amazon and possibly others. And so independent of the back-end infrastructure, Radical Pilot is able to work on any of these machines thanks to the interoperability layer known as Saga. Okay, and a whole bunch of kind of details more for your records. I alluded to a theoretical model of pilot jobs. That's what P-star is, right? And what I think will concern you will be of most relevance is some of these performance numbers. Remember, I talked about slicing and dicing along any different value of the number of cores, number of tasks, the size of each task. What I want you to just get away with is that this particular implementation that you're going to play around with in the next 45 minutes after the break allows you to submit jobs locally, as in not on these machines, but if you were actually playing on, let's say, this laptop, you could submit a large, that was a Linux laptop, I beg your pardon, or if you logged on to a supercomputer or cluster, you could submit a large number of jobs logged onto a machine, or you could submit in a distributed fashion, as you could from these machines. You could submit directly onto a cluster or a supercomputer that was physically distributed without any change in your operating environment, without any change in the set of tools that you were going to play with. In other words, you can submit locally but run globally. I repeat, you can submit locally without really realizing where your jobs are going to run, but your jobs might run globally. They could literally run anywhere. This is a concept that has again been talked about, I presume even in this school, but is often talked about. just want to reinforce that the radical pilot system allows you to have that capability of submitting locally and running globally, right? You can eventually, although we'll only play around with 1 or 2 pilot systems, or I should say instances of a pilot system, you could actually have order hundreds of these running and coordinating together. We're somewhat limited by the size of the resources we're going to play with, but there are people who run pilot systems or applications using pilot systems on literally some of the world's largest machines, 100,000 cores, and there they have order hundreds of pilots, those empty containers coordinated by a single job, and therefore, although we won't play with it, it's worth remembering that you can have hundreds and hundreds of these pilot systems being coordinated by a single application. So it gives you a sense of the scalability of this approach, right? We'll come back to this. Again, the number of tasks that should go within a single agent. If you remember, we had those yellow circles and then we placed one circle in one container. So there was one task per agent. The question that you should be asking is how many tasks should you put within the control of a single agent? The answer is, as always, it depends. If the tasks are going to generate a lot of data, generate a lot of communication, then the answer is be conservative. But if these tasks are highly non-communicative, then you can put up to thousands of tasks into one agent. And remember, you can put, as point 2 says, hundreds of agents. That tells you you can, at one instance of time, manage hundreds of thousands of tasks. That's already setting the scale for you. Order 10 to the power 5, possibly 10 to the power 6 tasks at the same instant of time. Remember, this is all about task level parallelism. I've proffered a system that is going to scale to support order 10,000, 100,000, possibly a million way parallelism for you, right? And obviously, if you need, even if these run on a single core, you need a million cores. Not many of us have access to a million cores at an instant of time, but we are fairly confident that there are reasons by breaking it up into multiple levels, as long as you kind of ensure that no one agent is managing more than 1,000 tasks, and there are no more than, let's say, 100 agents, then you can easily go up to 10 to the power 5 tasks. You might not get there if you put, let's say, too many tasks under a single agent's control. So you have to understand, as always with any system, what are the design decisions being made, and I'm trying to give you, through this very rough estimate, what the different design points are. And so therefore, when you do have a large number of tasks, you can then think of how to decompose them and place them onto this global infrastructure that you might be able to run on. Okay, and then there's a temporal dimension as well. In everything I've said right now, I've not assumed that these tasks run for a given duration. I've kind of conveniently glossed over that. Obviously, all this depends, all these numbers that I've been alluding to, 10 to the power 5 tasks, assumes that each task runs for a fair duration of time, fair within quotes, in the sense that, let's say, order minutes to hours. If you had tasks that were running for, let's say, seconds, the whole scalability problem becomes a bit different. Does somebody want to answer the question, why would the scalability be different if the tasks were running for, let's say, 1 second or less than 1 second? Why would this number that I throw at you, why would it be different? Anybody? Take a crack, take a guess. Please. Exactly, because then you're getting communication and latency bound, right? If you have tasks that are going to run for literally a second, then you're going to be generating a lot of traffic communication every second, as opposed to a steady stream of traffic, of communication that lasts for, let's say, an hour. So, thank you. Okay, so, but I'm just making an assumption here. Okay, so just to try to give you one simple example of running only 4 pilots at the same time, but each pilot approximately 100 cores, 96 to be precise, on 4 distinct supercomputers in the United States. 1 on the West Coast, 2 on the East Coast, 1 in the middle. This is an example of 4 different colors. As you know, each pilot goes to a different queuing system. Remember that whole objective of kind of putting a placeholder task, decoupling the task assignment, the task execution from the resource assignment. So you've got a large number of tasks, 300 and, well, in this case, order hundreds, and you don't know where these tasks are going to be executed. You submit to a single pilot job system, which then submits 4 different pilots to these supercomputers, as indicated by these different colors. These different pilots start at different times, varying over, let's say, half an hour to an hour. And when the pilots begin, they then start consuming tasks. In this one simple example, all I want to show you is that although you submitted 4 different pilots on 4 different supercomputers, because the variation in the startup time going through the queue was so large, 2 pilots consumed all the tasks, and by the time the 3rd pilot became active, there were no tasks to be had, right? So I'm sure you've got friends like that who suddenly become active after all the work is done. Think of these last 2 pilots as examples of that. In this case, the queue waiting times on those machines were much higher. And lots more detail to say that you can manage, you can introspect the state of every task that you've submitted. And again, we don't want to get concerned with the details here, because we want to go talk about the specific application. But the use of this tool allows you to not only get everything done, but come back and understand which task went where, when, and why. Something which can be very important for provenance. Okay, so 2 quick things. I've kind of made this almost seem routine that you can go over 4 different supercomputers, very distinct, not worry about the architectural and the middleware differences between different machines. Yes, it has been engineered for being able, Radical Pilot has been engineered to not be dependent on these systems differences, but it's important for you to be aware differences exist, and for you to be aware how these differences are hidden from you. So remember, the goal here was to try to give you a common conceptual model for how to execute tasks, but also to give you something that in an implementation sense was also common, independent of different machines, architectures, and middleware. And this is really trying to now, this slide and the next slide speaks to how that implementation is made common and uniform. 2 levels. The first level is that the pilot agent has to be aware of the architectural nuances of every supercomputer or cluster. Remember, there's a reason why supercomputers are supercomputers. They make certain choices, and it is in those choices, and obviously the high performance aspects, that they are able to support specific performance requirements. Remember, the specificity versus generality the specificity and performance is kind of 2 different dimensions. Specificity, let's think of generality as one dimension and performance as the other dimension. Most supercomputers get performance as a consequence of being as opposed to being general. The pilot agent understands architectural, able to, I think this mic is dying on me, is it? Okay. And the pilot agent accepts and understands the specificity of the architecture and does the translation. So you need an agent that is different for every different architecture that you might encounter. And that is the point at which the architectural differences are hidden from you, but that is also the point at which the specificity of that architecture is utilized in order to give you performance. The second level of if you will, infrastructural homogeneity is provided by the Saga layer, which I've alluded to several times. And what the Saga layer does is provides a common API to all the different, let's say, batch queuing systems. You've heard of PBS, you've heard of Slurm, you've heard of SunGrid Engine, you've heard of Torque and variants LSF. They are all essentially similar, but all differ in minor ways, which can be quite cumbersome to manage. There's also a difference in the way data is moved, the way data files are handled. That heterogeneity of the middleware is captured and standardized and made uniform through the standardized interface called Saga, which is again something that has been around for 4 to 5 years, and Radical Pilot utilizes that. Combination of the agent and Saga allows the infrastructural homogeneity. Okay, so now let me quickly go in the last 5 minutes that I have, go into the science examples. And as I said, I want to end at that example of WRF, many instances of WRF. So again, I just want to remind us that this is not constrained to a specific domain. It's a tool. It's a general purpose tool. It's implementing very simple conceptual models of how to use high performance distributed computing for task level parallelism. So it is only natural that it be used for any given domain. And these are two different examples of how Radical Pilot has been used to help people trying to study, in this case, HIV, and provide potential very quick time to solution cure for such drugs for HIV. Various other ways in which Radical Pilot has been used. This is a replica exchange example. And remember, I talked about those 3 dimensions of dependency, heterogeneity, and coupling. In this lower case, there's a lot of coupling between replicas, which are also tasks, but we call them replicas because they're exchanging a lot of information. And some of the largest replica exchange simulations ever have been run using Radical Pilot. On the upper slide, image, what you have is not different replicas, but the same ensembles, but now many stages, actually 20 stages deep and some dependency, again showing you how, in this case, 2100 MPI level tasks simulations were executed over 20 stages. So about 100 simulations in any given stage and 20 such stages. And this consumed, I have the numbers, but order terabytes of data, and I think order 500,000 hours in terms of compute time. Okay, so now let's get to the real, I will end with the real example that I want you to see. So this is WRF ensemble mode. And again, just very quickly, the underlying scenario that was studied was the flooding in Colorado, pretty recent, 2014. Right? 3 hours of data. So lots of things to look here. So this, on the x-axis, is the number of ensemble instances, so the number of WRF instances that you're running. And you can see we start from 1 all the way up to, I think, to the power 6 is 64, right? And on the y-axis is the time to completion, and the different colors are the number of cores. So you can see, first of all, that as you increase the number of ensemble methods that you might execute over, so the time remains the same. So just take this point, for example. You can see that whatever this unit time is, somewhere in about, let's say, somewhere around 300 or 400 seconds, 100, this is about 200, and this is 300, so 250 seconds. For the same 250 seconds, you can then get anywhere between to 32 or 64 ensembles done. So what you've done is, by using more and more cores, you've been able to run more and more ensembles without changing your time to solution, right? And this is because now your Radical Pilot allows you to run more and more ensembles without introducing any overhead. So this is the first lesson. And obviously you can see that you can use cores, you can run more and more ensembles at a given, for a given fixed amount of time. Let's look at this from a different perspective. It's the same data, but plotted differently. You have on the x-axis now the number of cores, right? And these lines tell you the number of ensemble members. So let's just take, for example, 32, right? So what this tells you is the time to solution for a 32 ensemble members, that is 32 instances of Whorf Hydro, actually decreases as you increase the number of cores. And that's because, again, radical pilot allows you to get as many cores as you need. And the more cores that you have, quicker your number of the quicker the set of ensembles that you have will start executing and therefore finish in time, as in quicker and quicker. So I repeat, another way of looking at this is to take just take any time here. So let's again take the 250 seconds. If you draw a line this way, you can finish in the same amount of time more and more ensemble members, right? And all you need to do in order to make this happen is the radical pilot to acquire more and more resources. So what I'm trying to say in a nutshell over the last 40 minutes is task level parallelism is genuinely supported by radical pilot or the pilot concept, and in order, once you're able to utilize the pilot concept, you learn how to do so, you can, without any additional increase in the time to solution, you can run more and more instances of your Whorf simulation as long as you can get more and more cores, which, by the way, is the whole point of scalability. As long as you can acquire more and more cores, and let's assume resources are there for the taking, I've presented to you an abstraction that allows you to keep your time to solution constant, but run many more simulations for the same amount of time or over the same amount of time. Okay? And what we're going to do over the next 45 minutes is essentially get to become comfortable with this tool, which will allow you to run such simulations. Please, question.
Definitely, from the graph, it proves that number of ensembles is not a matter. So number of cores is a factor.
Exactly. So as long as you have the number of cores available, you can run as many ensembles as you want, right? As you can possibly fit. And you never have to change the way you're doing it. And importantly, as long as you get more and more cores, a larger number of ensembles will finish at the same instant of time or the same amount of time. Okay? Please.
But how often would you have a large number of cores available at the same time so that you can run simultaneously?
So this is 2 to the power 12 is 2,000 cores. And Christian, how many cores does SuperMOOC have? 155. So getting 2,000 out of 150,000? 155,000 is 1/75th, that is less than 2%, right? So one user using less than 2% of the machine, I would say be ambitious, try to get 20%. 20% is 30,000 cores. I hope you're thinking as you're getting excited at the very thought of running 30,000 cores for each ensemble member, approximately 16, and so that's approximately 200 plus ensemble members, right? Question?
What happens at 64?
What happens at 64?
It's very different.
Oh, that's my graduate student falling asleep at the computer and not doing his measurements carefully. No, that's just an example. In this particular case, there was an error in the way these simulations were set up. But I wanted to leave that there for completeness. It's not a performance bottleneck. That's what I want to assure you.
Because for the others, it's very perfect.
Right. So you have a good question here. Actually, what is happening here is you're reaching the scalability limit of a single ensemble. So if you look at that number, so this is 64 ensemble members, and this is 2,000 plus cores. So if you do the maths, that is each ensemble member is running on quite a large number of cores at that point, right? and the scaling of each ensemble member, because of the particular model, does not increase infinite, does not stay the same at very large core counts, right? So if you go to, let's say, 1,000 cores for a single ensemble member for the specific model, you'll start seeing a slowdown, and that's what's eventually going to kick in here. Any other questions, please?
Talking about the scalability, did you have any experiments with some other program other than Word?
So for the concern of this community, the answer is no. But as I try to show here, in these examples, we've used a lot of molecular dynamic simulations and fluid dynamics and others, right? Genomics. And so the quick answer is, for hydrometeorology, WRF is the only one we've looked at, but we've done, I'll just throw some names, it may mean something to you. NAMD, AMBER, these are all very famous molecular dynamic simulations. And also just kind of going forward, try to show you some other examples of k-means. Again, some of you may know what the k-means is. So many multiple k-means simulations. So in a nutshell, your question is a very good question. I want to point out that the task level parallelism is valid for any task, whether it be WRF, whether it be molecular dynamics, fluid dynamics, or what have you. Okay. And so, in a way, I'll use this to end. Basically, what I said, that once you've understood the concept of, let's say, the conceptual ideas underlying task level parallelism, once you've understood the tool that is the radical pilot, you should be thinking of ways of extending and utilizing this. And that's what really is the point of the libraries and toolkits that utilize the radical pilot. So they don't expose radical pilot to the end user, as I'm going to do to you today. They hide it, and then they're able to do even more sophisticated quote-unquote workflows, or in the case of some data-intensive applications, they are then able to support a large number of analytics applications without ever exposing these concepts. But that, again, should come as no surprise, because that is the whole underlying rationale for having an abstractions-based approach, and in this case also a standards-driven approach, which then gives you the collective power of high performance and distributed infrastructure. With that, I say thank you for your attention. Let's take a 15-minute, 20-minute break. You wanted to make some suggestions